We've seen how to do enumeration to solve the inference problem on belief network. For a simple network like the alarm network, that's all we need to know. There's only 5 variables, so even if all 5 of them were hidden, there'd only be 32 rows in the table to sum up. From a theoretical point of view, we're done, but from a practical point of view, other networks could give us trouble. Consider this network, which is one for determining insurance for car owners. And there are 27 different variables. If each of the variables were Boolean, that would give us over 100 million rows to sum out. But in fact, some of the variables are non-Boolean. They have multiple values. And it turns out that representing this entire network and doing enumeration, we'd have to sum over a quadrillion rows. That's just not practical. So we're going to have to come up with methods that are faster than enumerating everything. The first technique we can use to get a speed up in doing inference on Bayes nets is to pull out terms from the enumeration. For example, here, the probability of B is going to be the same for all values of E and A. So we can take that term and move it out of the summation. And now we have a little bit less work to do. We can multiply by that term once, rather than having it in each row of the table. We can also move this term, the P of E, to the left of the summation over A, because it doesn't depend on A. By doing this, we're doing less work. The inner loop of the summation now has only 3 terms, rather than 5 terms. So we've reduced the cost of doing each row of the table, but we still have the same number of rows in the table. So we're going to have to do better than that. The next technique for efficient inference is to maximize independence of variables. The structure of a Bayes net determines how efficient it is to do inference on it. For example, a network that's a linear string of variables, x1 through xn, can have inference done in time proportional to the number n. Whereas a network that's a complete network where every node points to every other node, and so on, could take time 2 to the n if all n variables are Boolean variables. Now, in the alarm network we saw previously, we took care to make sure that we had all the independence relations represented in the structure of the network. But if we put the nodes together in a different order, we would end up with a different structure. Let's start by ordering the node John calls first, and then adding in the node Mary calls. The question is, given just these 2 nodes, and looking at the node for Mary calls, is that node dependent or independent of the node for John calls? And the answer is that the node for Mary calls in this network is dependent on John calls. In the previous network, they were independent, given that we knew that the alarm had occurred. But here, we don't know that the alarm had occurred. And so, the nodes are dependent because having information about one will affect the information about the other. Now we'll continue, and we'll add the node A for alarms in the network. What I want you to do is click on all the other variables that A is dependent on in this network. The answer is that alarm is dependent on both John and Mary, and so we can draw both nodes in, both arrows in. Intuitively, that makes sense, because if John calls, then it's more likely that the alarm has occurred, likely as if Mary calls, and if both called, it's really likely. So you can figure out the answer by intuitive reasoning, or you can figure it out by going to the conditional probability tables and seeing, according to the definition of conditional probability, whether the numbers work out. Now we'll continue, and we'll add the node B for burglary, and ask again, click on all the variables that B is dependent on. The answer is that B is dependent only on A. In other words, B is independent of J and M given A. And finally, we'll add the last node, E, and ask you to click on all the nodes that E is dependent on. And the answer is that E is dependent on A. That much it is fairly obvious, but it's also dependent on B. Now why is that? E is dependent on A because if the earthquake did occur, then it's more likely that the alarm would go off. On the other hand, E is also dependent on B because if a burglary occurred, then that would explain why the alarm is going off, and it would mean that the earthquake is less likely.